This is the most inclusive course on cotton fiber to fabric quality and manufacturing. It reflects more than 30 years of experience by one of the top scientists and utmost experts in the field of cotton research and textiles. Please be aware that what you will see is only very small pieces of some parts of the course. This course is over 40 hours in total. As you will see, the course uses direct teaching by the speaker, slideshows and real videos of all processing from harvesting and ginning to spinning and weaving. The course comes with all videos and hard copy of slideshows. An e-copy of one of Dr. Elmogahzy books also come with the course. Again, these are only few clips. A complete course should be ordered via Amazon.com using the title, the author, and the code number of the course.
The first part of this course is an introduction of critical concepts of fiber to yarn engineering and cost optimization. The second part deals with fiber characteristics such as fiber fineness, fiber length, fiber maturity, fiber strength, neps, and cotton stickiness. The third part deals with yarn characteristics such as yarn count, twist, strength, irregularity, and imperfections. All characteristics are discussed in the context of measurements and impacts on fabric quality. The fourth part deals with fiber processing, starting with harvesting and ginning and going into cotton mixing and blending. All stages of spinning preparation including opening and cleaning, carding, drawing, combing, and moving are covered in great details. Different types of spinning such as ring spinning, compact spinning, rotor open-end spinning and friction spinning. The course will also cover effects of yarn and fiber characteristics on textile fabrics.
The different types of dimensional characteristics are fiber length, fiber fineness, cross-sectional shape, and specific gravity or fiber density. And here we mean bulk density. The first characteristic we will talk about is fiber fineness. Now, the reference method of fiber fineness measures is the diameter of the fiber. So if we can measure the diameter of the fiber, then we can determine the fineness of the fiber. Large diameter would mean coarse fiber, and fine diameter would mean fine fiber. Well, we would hope that we can measure that on a routine basis and in a rapid manner. But the problem with fiber diameter measurement is that it basically requires microscopical work. We have to do a great deal of microscopical analysis in order to measure the fiber diameter accurately. And that will not be a great challenge because one can use optical techniques, for example, which are much faster than your typical offline microscopical analysis to measure the fiber diameter. But there is another challenge, and that is the fiber. All fibers are not typically rounded like the one that you see here on the screen. Very few fibers are rounded or circular. The majority of fibers are not circular in cross-section, except in synthetic fibers, and even in the synthetic fiber production, they make fibers of different cross-sectional shape. Fiber length is the second most important basic fiber characteristic. I would not say second, it's really along with fiber fineness and the length are extremely important. There is no contract of purchasing any type of fiber without specifying the length and the fineness. Fiber length is a measure of fiber extent along the fiber axis. Typical values of fiber length, in case of cotton, we may have a length ranging from 0.4 to 1.5 inch. In case of wool, from 1 to 16 inch. In case of flax, 5 to 20. And of course, just like in case of fineness, man-made fibers can be cut into any length. And you need to keep in mind here that we have short stable spinning, a cotton-like, where the man-made fibers will be cut to an inch, inch and a half, and we also have long stable spinning, which is the wool-like, where synthetic fibers will be cut down to lengths of 4, 5, 6 inches. So the man-made fibers can be cut to any length depending on what stable system or spinning system is used. The APHIS does an excellent job in doing that. Optically monitor the fiber length and give you a complete fiber length distribution. Look at this. This is a typical output of the APHIS, where you have a complete profile of the fiber. Here is the fiber length values. Here is the percent frequency of the fibers. And looking at this graph will provide you with a complete idea about the range of fiber length in the sample. You need to pay more attention to the graphical outputs of the APHIS. Here is the diagram by weight and the diagram by number. And you need to understand that if you look at short fiber content by number as compared to the short fiber content by weight, that the short fiber content by number will always be greater than the short fiber content by weight. The most accurate way is to look at short fiber content by number, especially if you're using this measure to set your carding machines or your opening and the cleaning units. Short fiber content by number. Certainly, if you are talking about setting the comber noils, then you must look at the short fiber content by number. Cotton maturity. The way cotton grows, you form the so-called primary walls first of the cotton cell. And the first thing that grows in a cotton fiber is the length, the fiber length. So the fiber grows in length first, okay? And the length has to be completed before the secondary wall start to form. And when the secondary wall start to form, the fibers start to thicken. So length grow first, and then fineness or thickness or meat on the fibers grow after that. So that's the order of growth when it comes to a cotton fiber. Fiber maturity is a result of a complex combination of so many factors. Okay? Not only that, fiber maturity is a very, very highly variable parameter. You will find different maturity levels within the field, within the same plant, within the same crop. I mean, fiber maturity is a very highly variable parameter. Keep that in mind. And that is why until we establish a very accurate method that is fast and reliable, it will be hard to expect the impact of immaturity sometimes in our process prior to processing the fibers. In general, maturity may be defined as the state of growth of fibers. That's a general definition. But in theory, and you need to understand the theory a little bit. I know I'm going to be talking about some mathematical aspects of fiber maturity here, but I think it's very important to understand that so you would know what do we mean by a maturity ratio today. And theoretically speaking, the fundamental definition of maturity that has been used is the degree of secondary wall development. Remember, we said primary wall developed first, and the length has to be completed, and then the secondary wall developed after that, where the fibers start to thicken. So the degree of that thickening is a measure of, or an index of maturity. And the way we define that fundamentally is very simple. We use the circularity ratio or the degree of wall thickening, as I will define in a minute. What you see here in these pictures is fibers that exhibit different levels of maturity within the same sample. And some of the characteristics of the surface of the fibers is the convolutions that you see here, which is twist, really. I mean, you look at the single fiber, single cotton fiber, and you're going to see that fiber being convoluted, twisted. You wonder why humans used twisting as a way to bind fibers in the yarn. You know, it's just a resemblance of how the fiber was made and how cotton fiber looked like. There are many methods, as I said early on, in the market today that one can use to measure fiber maturity. There is the Shirley FMT, that's fineness maturity tester. There is the caustic air test, which is a very old test, but it's still used as a reference test. And there is the NIRA reflectance analysis, and there are commercial systems now, the Analyzer 400. And there is the gold weight differential dyeing, which is an indirect method of fiber maturity. And there is also the APHIS. So we have in the market today many methods. And if that indicates anything, it indicates that we still do not have what I would call it a universal standard method of fiber maturity. That's why different efforts is being made and different directions is being taken.
NEPs, as you may know, can cause a variety of problems. For instance, NEPs composed of immature fibers reflect light in a different way than regular yarn with mature fibers. They will appear as a differently colored spot on the fabric.
NEPs which are on the surface of a fabric can cause unprinted spots during printing. This may be revealed later when a NEP falls off the fabric or garment.
Immature fibers, long, very fine fibers, weak, very flexible fibers are potential causes of NEPs in the process, in the fabrics. Not enough cellulose, not enough absorption of dye. Leads us to another problem, fabric barré. These are defects characterized by textural bands or color bands in the course of a knit fabric or in the filling direction in the weaving and the woven fabric. Fabric barré is a major issue. There are many factors that can contribute to barré, including variation in the mix, in the fineness, on the micronair, on the color. You want to watch out for the consistency in the micronair, and more importantly, in some cases, the consistency in the color. If you will allow, for example, the yellowness of the fiber, the plus P, to swing high and low, then you're more than likely getting yourself into major barré problem.
Here we see an actual automatic bail blocker. You can see that the tower or the blocking unit was working off a laydown. This is another picture, simulation picture of how different bales are laid down side by side. Here is the roller or the opening roller or the plucking roller working off different bales in the bale laydown. So you can very much see the operation firsthand here. Now we move to the combing process. The comber lab that we discussed, its features, is the material or the intermediate strand, the two-dimensional strand, that is fed to the combing process to make the combed sliver. So the combing process objective would be to convert the comber lab into a combed sliver of high quality, and that's why we have emphasized the criteria associated with the comber lab, because one thing we have to keep in mind, that is the combing process cannot do everything by itself, okay, especially at the very high speed of combing of 300, 350 or 400 nips per minute or cycle per minute that the combing machine of today has. So a great deal of preparation, cohesion of lab, lab weight, lab buildup, lab uniformity, evenness, all of these are critical factors that have to be taken care of before the combing process. Now we move on to the what I call it the yarn world. We give you an overview of the different types of yarns available in the market, which are results of the different spinning systems that we just reviewed. Yarns can be divided or categorized in many different ways. Stable fiber yarns, or commonly called spun yarns. These are yarns that are made of stable fibers, cotton, wool, and so on. That's one of the major categories when we mention yarns. We are talking either a spun yarn or continuous filament yarns. Spun yarns are made of discrete, small fibers, stable fibers. Cotton, wool, or actually synthetic fibers that have been chopped into small fibers. The second major category is continuous filament yarns, and continuous filament yarns may be fully drawn or pre-drawn, or the different levels of drawing may be used as subcategories of the continuous filament yarns. Continuous filament yarns can also be texturized, as we mentioned a few minutes ago, and this puts continuous filament into another category. So they may be pre-drawn, fully drawn, or texturized, and obviously, as we mentioned before, under texturizing there are many sub-classes of continuous filament yarns, mainly bulky yarn or stretchy yarns, as we mentioned before. In the marketplace today, you can see a lot of fancy yarns. Here is a scarf made entirely of fancy yarns. Here is another type of fancy yarn. There is a huge, wide range of fancy yarn available today in the market, and you can see from this picture the wide range of texture and the fancy appeals that makes this market a very unique, very fascinating, and a very stimulating market. As you can see here, there is a huge range of different types of fancy yarns. This session is about an overview of spinning or spinning systems. In this session, we will touch upon some of the common spinning systems that are used for spun yarn, stable fiber yarn, as well as for synthetic or continuous filament yarns. We will also go over some of the different categories and different types of yarns to give you an overview of the yarn world. It's very important to know about different types of yarns and all the possibilities that are out there. So with this, let us begin this session here, an overview of spinning systems. Diagram here. Our input material is the roving, okay? And as we mentioned in the spinning preparation, roving is a fiber strand, a thin fiber strand that looks largely like a yarn, except it's a very thick yarn. In English count, it's about 1 English count, which is relatively thick. It has some twist, because the idea here is to maintain the integrity of the strand, so the twist there is not to create any strength. The roving has to be handled, the roving bobbin has to be moved from one station to another. We have to wind the roving, and then we have to unwind the roving during ring spinning. The fiber strand coming out of the drafting system is then going into the consolidation area or the twisting zone. And as you can see here, the fiber strand via a guide line or a guide, we call it the pigtail, is threaded into the pigtail, and then it is going to the bobbin through a traveler that is dragged over a ring.
And the projectile, which pulls the precise length of the weft through the open shed. As you can see, this is a beautiful picture produced in a soldier, showing you how the projectile is taking the yarn. Look at the tension on the filling yarn the yarn has to take during weaving. Now, how the projectile gets the energy to pull the yarn or to shoot the yarn through the guide, this is done by an accelerator.